In this lesson, we'll be discussing solutions and applications of right triangles. So we're going to be solving right triangles. Well, now when we solve a triangle, it means to find every angle measure and every side length of the triangle. All right, so let's go for it. Solve right triangle ABC if angle A is given and it is 34 degrees and 30 minutes, or 34 and a half minutes, 34 and a half degrees, excuse me. And C is 12.7 inches. So one angle is given and a side length. Actually, two angles are given because they told us it's a right triangle. So we know one angle must be 90 degrees. And here's a second angle, so I guess we just need that third angle. Let's draw a picture to get us started. I think a picture always helps. So if you can, try to draw a picture. All right, so you can see that angle C is given. Angle C is 90 degrees, right? I noticed that our textbook puts the right angle at angle C each time. But nevertheless, one angle is given, 90 degrees, because it's a right triangle. This angle is given, and so we need angle B, all right? I think we can find angle B easily because you and I know that the sum of the three angles within any triangle must be 180 degrees. So what we can do is we can subtract angle A and angle C from 180 to leave us with angle B. So following that thinking, we find that angle B is 55 degrees and 30 minutes. All right, we have all the angle measures. So one of the angles is 90 degrees. They told us that when they told us it was a right triangle. They gave us angle A, and now we know angle B. All right, so we need the side lengths. We know the hypotenuse is 12.7 inches, right? That was given. We need the side lengths. So I'm going to use the given angle, right, and the given side, which is the hypotenuse, to find both A and B. I'll go for A first, I don't know, just because. Notice that A is opposite the given angle, side A is opposite the given angle, and the hypotenuse is given. Remember that sine, the sine function, has to do with opposite over hypotenuse. So I will take sine of the given angle and say that it is equal to A over C. So that means sine of 34 degrees and 30 minutes is equal to A over 12.7. To solve for A, I'll just multiply both sides by 12.7. So I'll get 12.7 inches times sine of 34 degrees and 30 minutes. And we find that A is approximately equal to, oops, wrote down the wrong one. A is approximately equal to 7.19 inches, approximately. What I do is I use three significant digits here for the final answer because I know I have three significant digits in the given information. So three significant digits, that's very important. All right, the side that's missing is B now, right? And this is the side adjacent to the given angle. So this time around, I'll use the cosine function. The cosine of the given angle is adjacent over hypotenuse. So we get cosine of 34 degrees and 30 minutes is equal to B over 12.7. And again, to solve for B here, we'll just multiply both sides by 12.7. So 12.7 times cosine of 34 degrees and 30 minutes, round to three significant digits to get that B is approximately 10.5 inches. Also, don't forget the units when you're writing down your final answer. This triangle is solved because every angle measure is now found and every side length. Before we move on to the next triangle, I wanted to point something out to you. Notice that the largest angle is 90 degrees. The intermediate, the middle valued angle is angle B, and the smallest angle is angle A. Notice the largest side is side C, the middle valued side is B, and the smallest side is A. In other words, the largest side should be opposite the largest angle. The middle valued side should be opposite the middle valued angle, and the smallest side should be opposite the smallest angle. When you are done with your problem, you may want to confirm that this is true for every triangle you solve. A new example, solve right triangle ABC if side A is 29.43 centimeters and side C is 53.58 centimeters. All right, let's draw a picture. Now, in this example, notice that this leg is given to you, and this leg, which is the hypotenuse, is given to you. So this is the side length that's missing. We'll find that side probably using the Pythagorean theorem. But notice that these two angles need to be found, angles A and B. We know C is a 90-degree angle. This is a right triangle after all. So what we're going to have to do is we're going to have to use a trig function in order to find angles A and B. Now, side A is given, and side C is given. And so notice that with respect to angle A here, the side opposite and the hypotenuse is given. Opposite over hypotenuse, that is the sine function. So what I'm going to do is say sine of angle A is A over C, right? Opposite over hypotenuse. Sine of angle A, therefore, is equal to 29.43 centimeters over 53.58 centimeters, right? Sine of A is equal to, or approximately equal to, let's say that, 0.5492721165, something like that, right? And so this is obviously not angle A. We need to find angle A here. They gave us the output. We need to know the input, right? We need to know the angle measure that corresponds to this particular function value. So what we can do is what we were doing in an earlier lesson, that A is approximately equal to inverse sine of this number, right? The inverse sine function. So we'll write this number down carefully again. And when you punch this into your calculator, we find that A is about 33 degrees and 19 minutes. Now we're going to round to the nearest minute here. And the reason why is because we want 4 significant digits. We notice that there are 4 significant digits in the given information. So that's the least number of significant digits. So that's what we're going for here, 4 significant digits. So there's angle A. We still need angle B, but what we can do at this point now, because angles A and B are complements, you can just subtract angle A from 90 degrees, and that'll leave you with B. If you want, you can do something else. You can subtract angle C and angle A from 180 degrees, and that'll leave you with angle B. But it'll be a little bit easier for me, less arithmetic, if I just subtract angle A from 90 degrees, acknowledging that these two angles are complements. Therefore, we find angle B to be approximately 56 degrees and 41 minutes. Okay, guys, the only thing that's missing is the side length B. But we have the Pythagorean theorem that says a squared plus b squared is equal to c squared. In other words, b squared is going to be equal to the square root of, or not the square root of, not just yet, c squared minus a squared. I was just getting ahead of myself. So here we have that b is equal to the square root of c squared minus a squared. That is to say, b is equal to the square root of 53.58 centimeters squared minus 29.43 centimeters squared. Now remember that we have 4 significant digits here, so that's what we're going to round to. So we're going to see that b is approximately equal to 44.77 centimeters. You remember from your algebra studies that whenever we take the square root of both sides like we did, we need the plus or minus symbol. But because we're talking about distance here, the length of a leg of a right triangle, we choose the positive square root and dismiss the negative square root. All right, this triangle is completely solved for. We know every angle measure and every side length. Now, in some applications that are to follow, we're going to be dealing with angles of elevation and also angles of depression. And so we want to make sure that we understand what those are. When interpreting an angle of depression or an angle of elevation, both are measured between the line of sight and a horizontal line. For example, this would be considered an angle of elevation. So this is the horizontal. A lot of times in applications it'd be the ground, And this is where you're looking, like you're standing here and you're looking up toward the top of a building or to the top of a mountain. So this is your line of sight, the line of sight, and this is the horizontal. Sometimes you're looking at something, that causes the angle to be here from a horizontal, called an angle of depression. We'll also be looking at some applications that deal with an angle of depression as well. Sometimes it shows up like, you're standing on the top of a building looking toward the bottom of another building across the street, or things like that where you're looking down. This is the line of sight and this is the horizontal. So let's look at some applications now that deal with angle of elevation and angle of depression. The angle of elevation from a point on the ground 15.5 meters from the base of a tree to the top of the tree is 60.4 degrees. Find the height of the tree. I think drawing a picture here is super, super helpful for all of these kinds of applications. So let's draw a picture. So here we have the angle of elevation is right here. It's from a point on the ground, right? This is the point on the ground, I guess, from where you're standing. From here to the base of the tree, assume that this tree is right up against this vertical here. So from here where you're standing all the way to the base of the tree is 15.5 meters. And the angle of elevation, read the question carefully, the angle of elevation from this point on the ground, 15.5 meters from the base of the tree to the top of the tree is 60.4 degrees. So this is your line of sight. You're standing here and you're looking toward the top of the tree. So this is your line of sight. That must mean the ground is your horizontal, okay? Line of sight and the horizontal. Okay, guys, we need to find the height of the tree, okay? I've labeled it as H. We have this angle. We have the side that's adjacent to this angle. Oh, I forgot to mention, notice that we have a 90-degree angle, right? We have a right triangle. So what function are you going to use now that you see that you have the side adjacent and the side opposite in this problem? This problem has to do with the side opposite and the side adjacent to this angle. I'm hoping that your mind is going toward tangent. Tangent is the function that has to do with opposite and adjacent. So tangent of 60.4 degrees would be opposite, which is H, over adjacent, which is 15.5. So what we can do here is solve for H, multiply both sides by 15.5. So H would be 15.5 meters, right, times tangent of 60.4 degrees. Now, this problem has 3 significant digits. If you look at the given information, you count 3 significant digits, and so that's what we're going to round to. So the height of this tree is 27.3 meters. Don't forget, meters is the units that we're using here. Not feet, not inches or anything like that. It's meters. So that's how tall the tree is. Isn't that great? Now look at this one. Find the angle of depression from the top of a 97-foot building to the base of the building across the street, located 42 feet away. As always, let's draw a picture. All right, I have my 2 fancy buildings here, all right? And then it says the angle of depression from the top of a 97-foot building. So I'm going to assume this is the 97-foot building here. So let me draw you 97 feet right there. Okay, I'll label that 97. From here, from the top of this building to the base of the building across the street. So then we're looking, this is our line of sight. Bam, right there, okay? And notice that it says that the building that's across the street, this one here, is 42 feet away. So here, this distance there would be 42. Okay, so I'm going to label that as 42 feet away. And also, I want to label the height of this building here 97. Okay, so we have a 97-foot building, and we have the other building across the street that is 42 feet away. Now, the question is, find the angle of depression. Now remember that the angle of depression is always formed, remember what we wrote down earlier, it's always formed by the line of sight and a horizontal. A line of sight and a horizontal. So in this case, the horizontal is here, folks. This is your horizontal up here, right? This is the horizontal, and then this is the ray or the line of sight. So this is the angle of depression. Let's call it theta, right? So let's call theta the angle of depression. That's what they're asking us to find. Now notice please that this is a right triangle, right? So they're not really asking us to find an angle that's within the right triangle. That's sort of a problem because all of our trig functions are defined by right triangles and the angles within a right triangle and the side lengths of right triangles. But this angle theta, the angle of depression, is outside of the right triangle. Well, I hope you remember from earlier studies that when you have a pair of parallel lines and a transversal, that alternate interior angles are equal. Please notice that this horizontal and the ground, right? The horizontal and the ground are parallel lines. And this is a transversal. That would make theta and this angle here, which is inside the right triangle, equivalent. These are alternate interior angles. So I'm going to label this for us. I'm going to label this alpha, okay? So theta and alpha are alternate interior angles, which means they're equal. So if we find alpha, we have found theta. To find the measure of angle alpha is to find the measure of angle theta. So here's alpha. So here we go. Notice that the side opposite and the side adjacent of angle alpha is given. So opposite over adjacent. All right, we'll use tangent. Tangent of alpha is equal to 97 over 42, opposite over adjacent. So then tangent of angle alpha is equal to 2.3095238. Okay. Notice that we're going to use two significant digits here because that's what's given in the problem. All right, so let's use an inverse trig function here. So we're going to say that inverse tangent, right? Alpha is equal to inverse tangent of this function value. So when I use inverse tangent now on my calculator, I get that alpha is approximately 66.587888583 degrees. But remember, we want to round to two significant digits. So in this case, I'm going to round this to 67 degrees. That's the measure of angle alpha in our diagram, which is also the measure of angle theta, which is the angle of depression. Isn't that great, everybody? We're able to solve an application like this one, right? Standing at the top of a building, looking at the bottom of a building that's across the street, and that angle of depression is about 67 degrees. All right, this is the end of this lesson. We'll look at more applications in the lessons to follow. So catch you later.